Started.
Okay, Andrew, we're on camera.
I need to apply my makeup. Fortunately, Predrag can review the footage, so he knows about this conspiracy. So,
Predrag, if you're watching that, just know that I got this message out of the matrix from your future self, and this is a very important message. The message is Adam is like the coordinator for Matrix. He listens to everything and he knows everything. I guess there was an imposter coming in and maybe just playing with my computer. It's very, very dangerous business. You have to be careful.
Morning. What's new?
Adam's freedom of speech has been suppressed. But we actually think he's an agent of the Matrix, and so he's actually listening to us.
Yeah.
Pretending to be.
My wife has been trying to find the mute button as well, so maybe whoever did it for Adam, my wife would like to talk to that person. But we must go on, and we have to do Fourier transforms for engineers, stuff I've done so far. It's too conceptual.
We have a lot of engineers today.
Well, Ulrich is there, so I'm happy. It's good enough for me. Just a brief review where we are from the last week, discrete world. You know, I brought you into a world of Fourier transforms. And number one, because they're immensely important. But second, I wanted to put them in a larger setting of linear operators for us matrices. And they come very natural out of discretization of space. So you make a space discrete. And to be able to put it on a computer, you even make it finite. So you make it some kind of hypercube in the simplest, most symmetric case. And then you have to compare what happens to the function as you move from lattice side to side. And that's done by using translational invariance of the problem, which is encoded in a shift or stepping operator. And derivatives are natural objects defined by Leibniz and Newton that have a good continuum limit, which do this job for us. But it turned out working with them is very awkward. And for that reason, one goes to the dual space of the problem, which we always do whenever we have matrices. We know that whenever we have a matrix, it has its intrinsic coordinate system, which is called its eigenvectors. And it acts, particular operator on this eigenvector space, acts by being reduced to numbers called eigenvalues in this proper eigen subspaces. So that's just a special case of a very general thing. And it turns out that translation operator has very simple eigenvalues. They're just roots of unity. And the translation all had to do with these roots of unity. And one defines a finite Fourier transform as a sum of discrete values on a finite set of original function multiplied by these roots. And that gives us representation of every function in a dual space. And that makes things that are very ugly, like derivatives and etc., it makes them very beautiful, because in a Fourier space, we replace the matrices. In this case, for Laplacian, I'm here compared to my two neighbors. That's what this operation means. It just replaces them by the eigenvalues, which are these roots of unity. In symmetric combinations, you get a cosine. And that means that in Fourier space, anything that can be constructed from invariant operations, translation invariant operation like shifts, becomes simple, diagonal, pretty. But often you don't see that when you read, let's say, books on quantum mechanics or on continuum waves, Green's functions, etc. You don't see this cosine. They are intrinsic to this thing having been done on lattice. So one way to get to the continuum limit is to say, well, when I look at elements of my Laplacian, only diagonal elements matter. So I look at, K, and it's in Fourier space, so it has a little tilde. It has some minus, which I insisted needed to be here. Now finally see why I needed them. It's a second derivative, so dimensionally it's 1 over length unit lattice spacing squared. Then rest is a pure number, it's cosine 2 pi and kth component, Fourier component, k subspace, going from 0 to the n minus 1. And then I'm supposed to replace unity. And this unity, remember, is me, and these two guys were left and right, and they combined in cosine, which is nice. It's a real function, so it's a real number. And an interesting question is to look at small k, because when n gets large, the k increase. And when you look at what these functions are doing, for small k, for example, for k equals 0, nothing happens. This cancels. That means the operation has 0 mode, and that means there is one invariance. So this is due to translation invariance. But if you take k equal 1, for example, and n is 10,000, this is a small number. So you're allowed to do a Taylor expansion of cosine. So the first term in Taylor expansions is a series of positive powers in a Taylor series of exponential, because cosine is the, every even term of it, while sine is every odd term. So 1/2 is because the first term in expansion is whatever is in here is squared. And the next term is, combinatorial of 4 is 24. The fourth power the next term dot dot dot, and we inherited this 1. So we can write this as plus, and now this a squared can be absorbed in here. This cancels this 2. So this is 2 pi over length k over a square plus stuff, which is I'm sorry, this is n, n to the 4th a squared. So this is much smaller than that if n is going. So we'll drop it and we'll make a low momentum approximation. So when you look at all these cosines, for small k, they change a little bit as you go across the lattice, but as the k increases, they pick up finer and finer structure. So you get the momentum. And now basically, you can give this thing a name. And conventionally, this is called a momentum. Or if it was a Fourier discretization of time, it would be called frequency. It's a dual variable to the length. And what happens to your propagator, and I will be, very messy with things here, but basically the only thing that survives here is this momentum. This minus became plus, so this is Laplacian is a positive operator, and this becomes m plus p squared, where I would have to do a few more steps. I'll do this now, but to move various normalizations around and absorb them, what I call mass. And that's what you will always see when you see propagator or Green's functions. They'll have this form. It's only when you study condensed matter and Brillouin zones, etc., you see that form.